Hi viewers, welcome to LMS Solution. Today we are going to see about step-by-step implementation of P&O MPPT in MATLAB. Thanks for watching our videos and kindly subscribe our channel and also click bell icon for notification about upcoming videos. So now I'm going to explain how to implement that P&O MPPT using Simulink block. Okay. So here we are going to use Simulink block for implementing that P&O MPPT in the MATLAB. So first I'm going to open Simulink block. That means for creating the model. So here we are going to use solar PV array and then boost converter. So first we need to fix the solar PV array, and then we have to design the LNCVL for that boost converter, and then we need to design that P&O MPPT for that solar PV system, and then next we have to that means we need to use PA controller, so that PA controller will generate that 2D cycle for that PWM generator, and then PWM generator generate the pulse for that boost converter to extract the maximum power from the PV array. So first I'm going to consider PV array. So I'm going to take PV array. And then I'm going to fix, that means I'm going to connect constant block for the irradiation and temperature. So I'm going to fix irradiation is 1000 and then temperature is 25. So next I'm going to fix the panel rating. So for example, I'm going for higher rating. That means I'm going to design the solar PV array for generating a 3 megawatt power. Okay. So I'm going to choose the panel rating. That means I'm going to choose the SunPower rating, SunPower panel rating. So you can see the details here. SunPower, you can search that. Yeah. So here you can see the different. I'm going to use the maximum power rating of that model. That means I'm going to use nearly 445, right? So I'm going to use this panel, right? Here you can see that that one voltage at maximum power point is 76.7. So I'm going to make some level. That means I'm going to use 5 panel, right? So if suppose I'm going to use 5 panel, means the terminal voltage is around 5 into 76.7, right? 76.7. So it's around 383. So 384 volt, right? So we not to make that, we not to generate 3 megawatt power from the solar PV array. So we need to make some parallel connection. So you have to find out number of strings in parallel. So for that, just you have to consider this current at maximum power point. So here is 5.8 times, right? The current is 5.8 times, and the voltage at maximum power point is 76.7. And then we have to calculate the number of valve string, right? So it can be calculated. So by using that, when you consider 3 megawatt power 3 power 6, okay, divided by, so first you have to calculate current requirement, right? So now we can see that we are going to consider five series panel, right? So each series panel will supply 5.8, right? 5 so it can supply 5.8 amps. So how many series parallel string connection will be connected in parallel, right? So here I'm going to divide with the voltage, that means 5 into 76.7. So when you divide this 3 power 6 divided by 5 into 76.7, so you will get current. So how much current will be we are getting from that when we are going to generate 3 megawatt power. Okay, then you have to divide with the current at maximum power point. So here 5.8, so I'm going to divide with the 5.8. Then so we will see that we need to connect this much amount of parallel strings. Okay, 1348, so we can consider 1349. So we need to fix 1349 parallel string. Then this PV array can generate 3 megawatt. So now we can check the PV IV characteristics of this PV array. So here you can see that, so it can generate around 3.001 megawatt, right? And the operating voltage is 383.5 for 1000 watts per meter square. For 500 watts per meter square, that operating voltage is 379.6, and power generated from PV array, that means maximum power point is 1.48 megawatt. For 100 watts per meter square, the operating voltage is 359.5, and it generates 281 kilowatt, right? 281.6 kilowatt, or else 0.228 megawatt. Okay, so now we fix that PV array, that means number of series and parallel string to generate the 3 megawatt power. So next we need to design boost converter. So I'm going to use that boost converter calculation. So this is the basic calculation, that means equation used for calculating L and C value for that boost converter. So here you got to fix that power 300,100, and then voltage of the panel at maximum power point at the standard condition is 383.5. So and I'm going to consider that switching frequency is 10 kilohertz, and then I'm going to consider the output voltage is 600. Okay, and then you have to calculate the maximum output current of the boost converter, and then you have to fix the ripple inductor current, and then you have to fix the ripple capacitor voltage, and then you have to calculate L and C. Just you have to execute this program, you will get that value of L and C, and then load resistance, and then duty cycle. So here I'm going to take RLC, series RLC branch, and then I'm going to rotate this model. Yes, I'm going to choose capacitance, input capacitance for that PV panel, and then I'm going to take same series RLC, and then I'm going to change detail as inductor, and then we need switch, right? So I'm going to take IGBT switch, so I'm going to connect in parallel. So next we need a diode, so I'm going to take a diode, then I'm going to connect here. So next we need capacitor, so I'm going to connect capacitance here, and then we need load resistance. I'm going to connect that load resistance. So here I'm going to change to branch type is R, and then we need to measure voltage and current in the load side. So I'm going to use current measurement in the load side and voltage measurement in the load side. So and we need to implement that P&O MPPT. So I'm going to use bus selector. So just you have to select bus selector. So bus selector is connected with the measurement of the PV panel. So here you can choose that PV voltage and current, and then remove this two signal and apply. So next I'm going to make that mean delay the voltage and current by some unit delay block. Now to find out the change in voltage and current, so I'm going to use change in voltage block, and then I'm going to use summer. So not to implement that P&O MPPT, right? So here I'm going to delay this voltage by unit delay block, right? So here you can change the symbol, right? Plus minus, and also I'm going to use same summing block for current also. I'm going to delay the current by unit delay. So here we are getting change in voltage and current. So next we need to find out the change in power. So I'm going to use product. So next I'm going to multiply change in voltage and the change in current. So here we will get the change in power. So next we need to make some decision, right? That means, so based upon change in power and then change in voltage, we need to change the reference voltage, right? So for that I'm going to use switch. So here I'm going to use three switches. So one for checking for condition of change in power. Another, these two will be used for check the condition of change in voltage. Okay. So first we have to check the change in power. If it is greater than 0, is connected to this. If it is less than 0, your comes here, right? So both condition, next we need to check the change in voltage, right? So the control input for this switch will be change in voltage. Okay, so next you have to based upon this change in voltage, so you have to increment or decrement the voltage reference, that means maximum power point reference. So here I'm going to take 0.01. Just you have to use constant block, and then you have to use gain block, right? So here you can multiply it with -1. If change in power is greater than 0, then we have to check the change in voltage. If change in voltage is greater than 0, so we need to decrement the reference voltage, or else we need to increment the reference voltage. If change in power is less than 0, so we have to come here, that once again we have to check the change in voltage. So after checking changing power, so here you have to take the, if change in voltage is greater than 0, you have to increment the reference maximum power point voltage, or else you have to decrement that maximum reference voltage. Okay. So next, after doing this one, next you have to calculate the reference voltage. So for that, here you have to use summer. So this output will be so saturated between two limits, and then the output also going to be delayed by the unit delay block, and then it going to be accumulated every time. Okay. So finally here we are getting that a change in reference voltage. So here we will get the actual voltage for the next stage, that means reference voltage for the next stage. Okay. So here we need to provide some saturation block, right? So we need to fix the saturation level. So for that, just you have to click the PV array and then click the plot, right? So here you can see that the voltage point variation is 383.5, and then for low irradiation is around 359.5. Okay. And also you go with the change in temperature also, right? So here you can see that the maximum voltage variation, once again, yeah, is 404, and then the minimum variation 356. Okay. So we can choose that voltage level is in between 400 to 350, right? So here I'm going to fix the voltage level. Maximum level is 400, the minimum level is 350. So here we will get the reference voltage. This reference voltage should be compared with the PV panel voltage, right? So just you have to change the sign, minus plus, and then this is going to be connected with the PV voltage. Okay. So next we need to use PA controller or PED controller. So here I'm going to use PI. So just you have to change that PI here. So after that we need to use PWM generator. Just you have to use PWM generator, and finally that PWM generator output going to be connected to the IGBT. So here I'm going to change the name as PWM, right? So just you have to take this block and then connect here. Just you have to change this frequency is 10 kilohertz, right? Next you have to change the value for L and C, right? Already we execute that program, so we have that value of L C, right? Just you have to change this L value and then just change the value of capacitance. So both input and output use same capacitance, and then you can change the load resistance. So next you have to use another block, nothing but power GUI. So you have to execute this block, right? And then you have to measure the power, voltage, power and current in the load side. So I'm going to use 3 input port and layout is 3. So first I'm going to connect voltage and then current, and then we have to measure the power. Just you have to multiply voltage and current, and same way we got to measure PV voltage, PV current and then PV power, right? Just you have to connect this one. Here I didn't do any tuning here. So first you have to check the response of the system. Okay, just I'm going to simulate this. The scope one is measuring the PV detail, that means PV voltage, current and power. So this is load voltage, current and power, right? So just I'm simulating this model. Now we can see that the PV power we are heading only 1.5, right? So because this is because of not tuning of this P parameter, right? So now I'm going to tune that parameter. So here just you got to change the sign plus minus, right? Plus minus, and then check the result. So now what happened, right? So it is extracting the maximum power. So that is because of this sign, right? Plus minus. Okay, just you got to change plus minus. Now you can see that is extracting maximum power, but what happened, right? It having more oscillation, right? So this is because of not, that means the PA parameter is not tuned properly. So we need to tune that parameter. Okay, so for that just you got to click this one and then click tune, right? So here you can click that plant, right? Plant and click identify new plant, and then click get IO data and then click simulate data. Okay, so here what we are going to do, right? We are going to identify the transfer function model for this our developed system, right? So that means, so here we are going to provide input and then here we are going to collect the output, right? So input will be duty cycle, the output will be error, right? So based upon this, we are going to make some transfer function for this by using that auto tuning method. So here I'm going to initial duty cycle, I'm going to fix 0.2, and then the duty cycle going to be changed at 2.5 second. The total simulation time is 5. So next I'm going to change the duty cycle from 0.2 to 2.4, right? So now we can see that initially is duty cycle 0.2, after 2.5 second change to 0.4, right? So we need to collect the data for this particular input. We need to collect the data. So I'm going to run the simulation. The simulation will be simulated for two times. After that we will get the error data here. So that based upon that data you have to identify the model in the form of transfer function. So here you can see that. So this is simulation started, right? So the simulation will be simulated for two times. After completion of two times, we will get the error data. So otherwise called identification data. So after collecting that identification data, we need to identify the plant by means of transfer function. So either we can use single pole or two pole or underdamped transfer functions. So we have to wait for completing that simulation process. So now the simulation process completed. Here you can see that we are got that identification data, that means error data. So now I'm going to accept this data, then close. So next we need to make that means we need to identify the plant. So we can identify the plant in the following structure: one pole transfer function, two real pole transfer function, underdamped transfer function. So here I'm going to select underdamped transfer function, and then I'm going to auto estimate the transfer function parameter. So after doing this one, right, so that the green is the identification data, the blue nothing but identified plant, right? So here we will get the transfer function parameter k, d, omega, and theta. Like this one is a transfer function. So the transfer function data is available here. Okay. So after identification, just you would apply. So after application, you can see that the dotted line, right, is the actual response already we have, right, in the plant. So this solid line nothing but after tuning, right? After tuning, we will get that value for P and I will be here 0.00618, here 0.2407, right? So here I'm going to take the value as it is. Okay, that means after update the block automatically it will be updated here, that kp and ka will updated here, right? So now I'm going to check the output of the PV, right? PV and the load side. But here also you can see that there will be oscillation in the PV voltage and current, and also there will be oscillation in the load voltage, current, and power. So so I need to further tune the model. So I'm going to delay the response, and then so now I'm going to delay this one. So now I'm going to update this. So here you can see this, there is change in the KP and KA. So now I'm going to check the response of the model. So now we can see that it will be at maximum point level, right? So I need to tune further, because now you can see that so there is no oscillation in the PV voltage, current, and power, and also you can see that so there is no oscillation will be very less in the load voltage, current, and power, right? So you can tune further, right? But now the response is very slow, right? So when you change this response, move this uh, cursor at this one, cursor to slower response. That mean it will take time to reach the maximum point. Okay. So and also we can change this response here, and then you can check the response. That means I change this to faster response, right? So update the block and then check the response now. So this is a way of tuning that PA parameter in order to get the maximum power from the PV array. Okay. So the PA controller is tuned by using this method. So auto tuning method. So you can after tuning will get the better results from the PV array. Okay. So this is the step-by-step implementation of P&O MPPT for solar PV system in MATLAB. Thanks for watching our videos. So kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you. Thank you so much.